sense. Okay. Welcome to week 7, a continuation of our plumbing system design. So let's talk about sewage and drainage today. So basically, right, the sanitary drainage system is designed to safely remove emphasis on safely, because there are different ways to remove, right? Safely remove wastewater and sewage from plumbing fixtures and discharge it to the municipal sewer, which is the city's large network of um, disposal, sanitary disposal, or the septic system, right? And or it could also be a treatment plant, right? Because these days you have wastewater divided into grey water, black water, where grey water is the water that can be treated and reused, recycled basically, but it may not be used for like drinking purposes. It can be for like irrigation or maybe flushing WCs, for example, right? So that is a case where a treatment plant can come in. But we are going to be focusing on doing it to either a municipal sewer or septic system. So let's go on. The key design objectives for designing this type of system are: one is to prevent blockages, right? So you have your pipes, they could get blocked. So to avoid that, and to maintain self-cleansing velocities, very important, right? Because these things fall under gravity. You do not direct gravity, but it's one of them. I mean, this the speed at which it is flowing through also helps to clean it, right? Then to prevent sewer gases from entering unoccupied space, good. Then to protect trap seals. As we go on, we'll see what trap seals are, right? And then it must comply with plumbing codes, right? It's actually very sensitive. These kind of systems are very sensitive, and it takes a little thing or a little mistake or error that will make you not to comply with plumbing codes. So with time, you get more um used to using plumbing codes, and there are some things you just know, right? So all these five add up to make it a safe removal of wastewater, right? So moving on, the system has three main parts, which consist of the sanitary drainage piping, which is the first part, then the vent piping, which has to do with how the sewer gases are removed from the system, and the traps and other accessories, which is still these traps as I spoke about here. So let's move on. Now let's start with this first one. So sanitary pipes carry wastewater by gravity, no pressure, unlike the supply hot and cold water that are coming in. Those ones, the pipes are usually full and flowing under velocity and pressure, right? But for sanitary, it doesn't usually flow under pressure. So that is why it's okay. Let's just go on. So sizing, that's why sizing is critical, right? Because if it's not sized properly, there could be blockages, or there could be slowing down or like stagnation, right? So key design principles include: the pipes must flow partially full, so it's never full, right? Imagine a circular pipe, right? Let me see if I can even find something. So you can see what I'm talking about here. So the pipe is never full, it's only like either half full or less. So it has to be a minimum of half full. So there has to be space for air to flow over the liquid, right? So another thing is that the minimum slope is required to maintain velocity. Yeah, velocity must be high enough to carry solids, but not so high that liquids outrun solids. So now let's see what these slopes look like, right? So if you go to this table, IPC, this, you see the different type of slopes available, which are here, right? So you see, this basically means that for every 1 inch in a horizontal direction, there must be a drop of 1/16 inches in the vertical direction. You see that this is the lowest and it's almost horizontal. So there's likely to be stagnation in this unless it matches the sizing. Of course, there's how to check that. Let's even go to this table and see what it says. Okay, you can see the table here in IPC 2024. I'm sure California's code has something equivalent, right? Okay, so these are the um slopes, and it works for these sizes of pipes in diameter, right? So most times in my design I use this one in the middle, right? Because of that is where like my sizing falls into. So now let's compare these different types of slope. You can see here that this 1/2 is the most extreme, and it is the closest to the vertical, and the liquid falls very fast here, right? So this is a case where if it is high enough to carry solids, in this case the velocity to be high, but in this case it will be low. So now it's good to find a balance, because if it is too high, the as you can see here, the liquids outrun the solid, because solids have friction and undergoing friction more than liquids, right? But if it's too low, there could be stagnation, right? It just needs to be high enough to just allow it pass. So that's why in most cases these are the most used, right? But then again, it also depends on the size of the pipe and the size of the system. If it's a very large pipe, it could be this that is in use, right? We'll talk about that more as we go on. So let's talk about DFUs. If you remember, when we talk about water supply, we came across WSFUs, which has to do with the supply fixture unit. So this one now is the drainage fixture unit, and it basically represents the volume of discharge in a fixture on the total sanitary system. Then the discharge frequency, how often, right, that discharge takes place, and then okay, the volume, the frequency, and then the probability of simultaneous use, right? So this value now, once you get it now, for it varies across different fixtures, right? And it gives an idea of what the flow out of that system looks like, right? So if you go to this table here, we can find more on it. Let's go to that table and see. To continue. So as you can see here, for the different fixtures, we have the corresponding DFU values, and you see that for larger type of fixtures, or fixtures that have larger flow, the value is larger. For example, this. So bathroom group is just basically a group of bathroom fixtures together. So let's look at clothes washers. This is like a washing machine. For commercial, is larger than for residential. Let's go down and see. One is just for little lavatories. So go down. Then it's also have for WCs as large as 6, right? Even though this is for like WC that are greater than 1.6 GPF, right? And the ones that are greater, I discovered, I found out that they are no longer really in production, so they've like gone out of um um phase, but that is not like part of our discussion for now. So you just go to this table and you read your value, and also you can also read the minimum size of trap. Trap has come again, right? We'll talk about what traps are. Okay, let's look at that again. Yes, minimum size of trap in inches. This trap is basically like the size of the the pipe that is coming out of that fixture. We'll talk about it shortly, pretty much. So now you see that those same values is what I filled in here, right? So now let's move on. Pipe sizing. So now the importance of DFE is that it enables us to size our pipes better, right? So the steps to doing that is that you identify all the fixtures. So obviously this is part of the pre-design step. So whenever you get a project, look at all the fixtures, right? Look at the layout and then decide how you're going to like design that system. So then you assign DFUs to each of the fixture. Yes, then you sum the total DFUs, right? And then you read from this table, which is just under this table. Let's look for that table, right? 710. Okay, this is it, right? So now when you get your total DFUs, you come here and find the value which is closest to, right? So for example, now if you get like maybe 35 or 36, take this 36 as your total, right? And then let me see, confirm that I showed you that. Okay, this is an example now. So you see this is like a layout of available fixtures in a building. So it came up to 11. So let's check what 11 DFU is going to give us. So 11 is somewhere here, right? So that means you are going to use a slope of 1/4 per inch, and then go this way, and then the pipe size for that, the main pipe that covers all that drains out all those available fixtures will be about 2 inches in diameter, right? If it was 36, now you see it has increased to 3 inches, and it is a different slope too, right? But if for any reason now you wanted to maintain one particular slope, because I mean the system is not just one straight line, there are branches, right? So you could want to maintain the same slope across. So that means you just stick to either this, or if you're using this, you stick to this. And then if you have to, maybe if you're sticking to this 1/4, you take 36, it will be somewhere here. Funny enough, it's still the same 3, right? The same 3 inches, right? And even if you go here, okay, this here, it will be 2.5, right? So yeah, okay, no, it's actually 3 here, because it's 36 and it falls above 31, right? So like I say, these are the ones that are most commonly used, but there are also certain cases where you get to use this. For example, you can see this is for a very large pipe, right? And when you have DFE that is this large, right? For example, the municipal sewer itself that consists of a long distance, and then maybe it receives drainage from a lot of buildings, right? So that can add up to this, or just a very large project that has a lot of drainage fixtures, right? So you can see that here this one applies across all, but this one is just only like minimum of 8, right? So now let's go back and look at this again. So you see how all of this works, right? This one works for like when the pipe is larger, right? And then this one works when the pipe is really small, because let's not even go to the reasons why. Okay, let's just talk about the reasons why, right? Because I mean, smaller volumes are likely to stagnate, just like a puddle like to stagnate at larger volumes. So if you have like this now, larger pipes, it most likely goes with larger volumes flowing through it, right? So even if the is not flowing fast, but there's still a continuous flow that is continuously pushing everything and moving forward, right? So these are like two extreme cases which you need to use only in specific cases that rhyme with the number of DFUs available. So let's move on. So now let's talk about venting, right? So venting maintains atmospheric pressure in the drainage system. You know how you have a pipe open on two ends, and if the pressure is equal, the flow in that pipe is constant, or is constant, right? But if one is exposed to a larger or lower volume lower pressure than the other, there's an instability in flow, or then the flow is no longer as stable as it was before, right? So that just introduces some level of disorderliness into the system, right? And remember I mentioned that the pipes are not supposed to be pressurized in the case of um, drainage pipes, and this is another thing, a factor that affects that. So let's move on. So venting protects trap seals. Traps have come up again, right? And we'll talk about it. Prevents siphonage. This is where the disorderliness of the flow comes in, because when the pressure is not controlled or is not allowed to escape, it tends to create some kind of turbulent flow within that system, right? And then even back pressure, because it wants to flow the air as the drainage is taking place, as it's flowing out, the sewage is flowing out, some gases are released, and these gases tend to build up. So if they are not released out as soon as possible, they will create some back pressure on that fluid and affect the whole system, right? And then it also allows the smooth flow of wastewater. I don't know if you've done an experiment where, if you have you're pouring water out of a carton or a container, if there's just one exit, right, the air is not replacing the water that's coming out, right? You notice the water is flowing um, turbulently, in a turbulent manner. But if you are able to create a hole for air to enter in while the water is flowing out, it becomes a more laminar flow, right? So that is what happens here. So every fixture requires a trap to block sewer gases. Now let's look at what this trap is. So as the name implies, trap because it traps air. So this is the fixture, a sink or a lavatory, and then this is the drainage. It's going into the drainage system. So now the when somebody turns on the water and washes their hand or whatever, it flows in here. Now this water trap is called a P trap because it's shaped like a P. This water trap prevents that bad air that forms while the flow is going out, prevents that bad air from coming out into the fixture, right? So it basically forms an air trap and prevents air from coming out, right? So now let's talk about it in terms of venting, right? So this is a fixture again. This is the trap. Now the water, dirty water or the wastewater flows out here and it goes down into the drain pipe, right? Then you also have another fixture that's coming out into the drain pipe. Now there's likely to be bad air or bad odor or smells or gases that form as these things that are happening, right? And now these traps prevent that air from escaping back into either of these places. This is also a trap here too, right? Prevents them from escaping. And now that air now that is within all this area, right, gets to go up out because air is light, it gets to go up and flow out through the vent. So this is a classical case of venting and explained with the use of traps. So they are working hand in hand to create that smooth flow. Now imagine this trap was not here, so the gases released will just be stuck inside here, and it's going to affect the smoothness or the stability of the system. So moving on. Now without vents, traps can be emptied, right? Because that siphonage you spoke of earlier, when there's no place for the air to go out, you discover that the one side pressure gradient takes place. One side pressure is greater than the other, and then that makes that water trapped here to flow out, and then the air escapes back into the system, which is basically this, the gases rather. Then the drainage becomes slow and noisy. Like I mentioned, that air now that is escaping, because when it goes in, air goes in with it, so that air gets to escape, right? So if air does not escape, it makes it to the flow of the sewage to be turbulent and unstable, and then causing noise and is not efficient basically. So let's move on, right? So now types of venting systems include um in the individual vents. So this is a case where each fixture has its own vent. So you can see here, this is one fixture, so it just has one vent going up like this. So this is an individual vent. Now common vent, two fixtures share a vent. Assume you wanted to save one pipe and then you wanted to bring this down here, so as it goes up, instead of going straight up here, it then goes here. For example, if these were the only two fixtures and you wanted to just vent it up straight through the roof, you wouldn't want to give them separate vents, right? So you bring it up, join it here, and then take it up. This is going to be a common vent in that case because it's serving more than one fixture. Now wet vent. Wet vent happens when you have moisture flowing. If you notice, there are different vents which is in broken lines, and it usually does not like it's not made to allow fluid or liquid flow through them. But there are cases where they called wet vents where the liquid can flow through, as you can see here. So if for any reason now you don't vent this fixture directly, okay, let's see here. In this case now, you see that the fluid, before the air begins to escape or the gases begin to escape up here, you see that there's a combination of liquid and fluid flowing through here, just like how it is in this case. So now that area where there's both liquid and gases flowing, that is known as a wet vent, right? Because vent actually meant for like gases to flow, not liquid. But there are cases where they have to meet, and any place they meet is called a wet vent, right? And they are important because you wouldn't always be able to vent directly from the top of your your fixture, right? So in a case where you have to like flow first for it vent, that is going to be a wet vent. You see here too, there's another wet vent, right? So now let's move on. Stack vent. Stack vent is basically this guy, this vertical guy that is going up into the roof, right? So then vent stack is a bit different. Vent stack is this one, right? So stack vent is just the ending. Vent stack is like what leads up to it basically. As you can see, this particular stack vent stack is serving all these fixtures here, serving these fixtures, and they all meet. Even this one here, they all meet and go up into the roof. Now, finally, let's talk about circuit vent. Right, circuit vent is used when multiple fixtures are on one branch, horizontal branch. This is that horizontal branch, right? So by the time you have one, two, if you have another fixture here, three, they are all on this branch now, right? It's known as a circuit vent because now there's like kind of like a circuit for the air to flow through. But now that circuit vent must have a release, so that's where the air escapes through. So moving on, let's talk about how vent pipe sizing works. If you understand how the main pipe, drainage pipe works, vent piping is a just a little change. So it's still based on DFUs, based on length of the vent, and based on the pipe diameter, right? Now, what just changes is that it is usually a minimum of 1.5, right? And then it cannot be smaller than half the drain size. So basically, like a standard, when you have your size of your drainage, let's look at that table again. You have the size of your drainage. Is it this? Yeah, so these are your different pipe sizes. So if you want to like attach a vent pipe based on the size of the selected pipe, you just select a vent that is around either the same size as that pipe or maybe slightly smaller by like half an inch, which is this, for example. So you have 3 inches pipe, drainage pipe, and then a 2.5 inches vent pipe, right? Now the main vent through roof is usually at least 3. So to be on the safe side, 3 is like a standard size for vent pipes, right? And this is because you're supposed to prevent frost closure. So in this place now, as much as water is not flowing through it or liquid is not flowing through it, there's still some H2O gases, right? And if it's not big enough, it can like form a kind of frozen layer or frozen blockage around this place, and then that defeats the whole purpose. So the larger the pipe, or the larger the stack vent, the less like that is to happen, right? So let's move on. So now let's go on talk about equipment sizing and selection, right? So we talked about some equipment for freshwater supply, like water heater and recirculation pump. So now in drainage system, there are also some equipments too, right? And they need to be selected and sized accordingly, right? So now let's talk about one, grease interceptors. So now they're usually used in commercial kitchens, right? Food courts, restaurants, to remove fat, oil, and grease (FOG), and to prevent sewer blockage. So grease is usually generated from cooking, right? It can also be generated from maybe engine rooms or stuff like that. Basically, anything that has to do with oil. You know that oil um, congeals when the temperature is cold, right? So all those, if it's in gas accumulates in one place and then congeals, it's going to cause blockage, right? So the purpose of this grease interceptor is to trap it or intercept it and then prevent it from continuing its flow. So let's look at an example, right? So this is a kitchen sink, mostly in commercial kitchens where the volume is way higher, right? So you see the drainage pipe out of it, and then you see our trap here. This is an S trap, and then you go on, you see venting is taking place, right? Now this is our interceptor. So that water that is laden with grease flows through this, and then the grease is trapped here. So this is like a separator, separates it, and then only water flows out. So when this gets full, it is cleaned, right? So you can see you see in this case now, the grease interceptor is buried underground. Just the top is visible to enable it to be emptied accordingly, right? And we also notice it is vented, very important in designing these systems. As many, not like too many, but as many opportunities as you need to vent, you vent, right? Any place that is likely to have a gas buildup, you put your vents. So this is what a circuit vent looks like, because it forms a circuit around it, and you see it is still vented up. So there has to be like a place for escape, right? You notice even the pipe that is being released is also having its own, is also being vented, right? Although it's not like a standard vent, but it is vented too, right? So this is another arrangement of a grease interceptor where it is kept above the ground level. So I mean, depending on which is more convenient for the site, one of them will be chosen. But you know that everything else remains the same. This is a two compartment sink, and then you notice it is still routed here, right? So let's move on. So now how to size this particular grid interceptor. Now I I international plumbing code doesn't have a particular table where you have like maybe GPM or DFU and then you add up based on that, right? But I was able to come across this particular company that has their own um manual for this, right? Okay, this is them here, their own manual for this purpose. Okay. Oh, this is not the right thing. Okay, you should go through like information on this, right? Let's look for that. Okay. Okay, good. Now, remember that we have fixture outlet sizes, the trap sizes, right? So now that trap sizes is the diameter of that pipe, and it knowing that size gives an idea of the amount of fluid that can flow through it at a point in time, right? Or over a duration of time, right? Or the speed, the flow, right? Now, what they did here is that they assigned different values to the different um, sizes, and then they also assigned GPMs, right, to those values, and then they not even rounded it up, right, in this case, right, because it could be more for some reason, maybe rare, but it could be more, right? But to be on the safe side, they rounded it up. And then they now went ahead to like recommend there are different types, right? This is actually very good because as I was researching, I couldn't really find anybody that did something this good. I saw some people that used volume, right? But volume is not very using volume of the sink or this the fixture source is not very efficient because you can't always know the size. There are different sinks, and each of them have like different sizes. So you can't always know the size of the sink except you're on site. So this is even better because I mean they all have fixed trap sizes, right? So it gives like a more informed guess. Okay, so that's how you size. So even if you don't want to pick their own, right? You just get the number of fixtures that are going to that interceptor because in this case it's just one, but it could be more. In the kitchen, there are like way more fixtures. It could be more. So you get the total number of fixtures, get the total number of GPM from that. Just like when we are sizing the pipe, and then you choose the right size of um, grease interceptor. Now, another thing to take into consideration is the retention time because this is what enables the grease interceptor to be more efficient, right? So 30 minutes minimum, right? Because and the longer it is, the more efficient because when the liquid, the mixture, okay, no, it's not really a mixture because it's not together, but basically when the fluid, the two fluids, let's call it a mixture, goes into the green interceptor, as it's able to sit for a while, right, is able to separate better, right? The temperature drops, it's probably at a higher temperature, but temperature cools down, and then the grease separates from the water, and then the water flows out. But if it doesn't sit for a long time, when it is still, and also when the liquid settles, right, is able to like separate better. But if it flows in and it's still turbulent and does not settle down, it's likely to also flow out. A lot of grease is likely to flow out too. So I mean there are some that will tell you some sometimes you can also size with 1 hour, you could size with or even more, right? But it's usually around 30 minutes or an hour, right? So as you can see, 30 minutes. So you basically just multiply your total GPM by 30 minutes because this is gallon per minute. So to get the amount of the volume we need, just multiply it by minutes, and that will give you like total volume of gallons that you need for your this thing for it to work properly, right? So now let's talk about another equipment which is called the sewage ejector or a lift pump. So this one is usually used when we are pumping out of a lower um, location. So I mean, in most cases we've seen they are just flowing out and down into the ground because of the slope. But there are cases where in a basement, for example, right, is lower than the existing system. So there's need to like pump it up. Right? This is not very common, but it is common too. So it may not even be directly sewage. It can just be another place where maybe water gathered and you need to like get rid of it, right? So that is where this is used. And like we said, when sizing things that deal with pumps or pressure, you have to consider the dynamic head, right? So you take the number of DFUs of flow. This gives you the volume, an idea of the volume that's flowing into that place, right? And then you're able to size accordingly. And then you check the solid handling capability because the pump has to be able to work with solids. If it's not a pump that can work with solids, it will spoil, right? It will get damaged. Then another thing to consider is the standby arrangement. I've spoken about this before, where especially in commercial buildings, any equipment can spoil anytime, right? And it's usually good to have one on standby, right? It's more expensive. It is expensive, right? And some clients may not like agree when you tell them that they have to buy two at a time, but it helps them in the long run because when and if one spoils, the other one can like kick into action and work while they replace it, and it helps greatly to reduce downtime. So it's a standard, or it's important that size when you size and select one, you find a way to indicate that they should put at least an extra equipment for that, right? So now let's talk about floor drains and cleanouts, right? These are not exactly fixtures, but they are part of the 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 drainage system. So floor drains are usually placed in wet areas, any place that gets tends to get wet, right? And cleanouts are provided for maintenance access. And so you please just look up what these things are to give you better understanding, right? I'm sure you know what a floor drain is. It's just cleanout that might be a bit tricky for you. So floor drains are just they must be trapped and vented. Like I said, as many places as even if it's a wet vent, even if you don't want to give it like its own special vent in a wet vent, you must find a way to vent or floor drains, right? But clean outs, okay, talk about clean out shortly. So at least one floor drain is required in every room that is susceptible to potential flows, overflows, and spills, right? Especially in public buildings, right? Then clean out is at the base of the stacks. You know, you saw what a stack is, a vent stack is. And then these are like some code requirements. This is not all, so you still gonna look up the rest, right? So now is to summarize when designing for sewage and drainage, right? So you identify your fixtures and their locations on your plan, then you assign your DFUs, right? And then lay out your piping, right? And then size your pipes accordingly, and then you design your venting, right, to protect traps, right? So I mean, venting and traps they go hand and they work together to like keep all those bad gases out of the building. Then you check your codes too. I mean, with time as you design more, you know all these codes by heart, and then all these sizes too. Then you check equipment that needs to be selected. So why this is necessary is because there are some cases, it's only in specific cases, like if you're designing for like a commercial building that has a large kitchen or a commercial kitchen, right? That is when you put interceptors. You can't put in grease interceptors everywhere, right? Most residential buildings don't need it, right? Because the volume is not worth the expense. But when you have like large producers of grease, a building that produces large amount of grease, it is better to include and size your grease interceptor. Pump too. If you don't have any basement or you don't have any lower location where you need to pump something out of, you don't need that pump, right? Unless you just want to increase flow. And then again, this particular type of system does not usually require pressurized flow too, right? But then you are the engineer. If your discretion calls that you need to install one of these, even though it's not exactly that picture, go ahead and do it, right? As far as it contributes to an efficient and safer system. So finally, you coordinate with your architect and your structural engineers too, because at the end of the day, if what you're doing clashes with what they are doing, it's going to be a problem, right? So, so now just on research on the. I also mentioned something else that is more about floor drains, clean out, right? So you research on these, the limitations and the uses, the applications, basically limitations applications of this. Just basically read up on what they are so that you can have better understanding. So let's see if we can. So this is a project we've looked at before. We've sized. This is a coffee shop, a small coffee shop. We've sized the mechanical system. Designed the mechanical system. We've designed the fresh water plumbing system, water supply plumbing system. And now let's look at how the drainage for this is going to go. The drainage system for this is going to look like. So first of all, as usual, look at your building, your project, and take notes of what you should do. This is a cold room, right? This is just a bathroom. So this is a very small building. So normally it's just a coffee shop. So it still falls under commercial kitchens, right? Even though in this case there's no need for a grease interceptor because there's little to no release of um grease, right? There's no oil cooking or anything of that nature in this, right? So what else? They have just one bathroom, and I'm using this because it's a very simple project to help you to understand better. So let's design for this. So now this cold room is like it's quite large, right? If you notice, refrigerators, right, or freezers usually have a drain pipe or a drain portion or a drain whatever, right? That means when ice is formed inside that place, it needs to drain out when condenses. Is it condense? When it melts, not condense. When ice melts into water, it needs to be removed. It's not clean water, right? So I will need to put floor drains in this place, even though it was not stated for me, but my discretion. And then I'll need to also plumb the system here. So let's do that quickly. Let's go to do we have a sewage? Okay, we have a sewage layer. Okay, so let's quickly do that. So I'm going to use lines. So I want to put my floor drain somewhere here and here, equally spaced out. And I want my system to travel around this place to here. I mean, it can actually go through here, oh, right? It can actually go through here. Let's even do that. Let's even do that because, like I said, the shortest distance possible. Oh, I know why I decided. Okay, let's just do it. Let's just do it. So this goes like this out here. So this pipe has a slope of 45 degrees. This is how we do that. Okay, 45. Okay, this should not be. Oh, this is 90 degrees. So this is, if you see, oh, it shouldn't be. It shouldn't be. Okay. No. It snaps to 45, and then it goes up. So this is just my own discretion. I mean, you as the designer could decide to do something different. This is 45 and then out. That's another thing I didn't mention, right? Usually there is, unlike cold water lines, that is just like sharp 90-degree bends because it's under pressure, so it doesn't really matter much. This one now, if it's sharp, this place could be like where the water gets to stagnate, right? So it's good to avoid stories that touch. Right, okay, let's move this down a little. Mm, okay, okay, somewhere here. Okay, so that I can capture this will cover like maybe this half of the system, and then we can also just copy this because I need something similar up there. Right, so you move it somewhere here, this other half, just to cover it. Right, so now our floor drain releases water into this system, right, and the floor drain will also have their own traps too, right? Because within this pipe, there's likely to be bad gases that we don't want to enter our building, so there will be traps. Right now, to route the piping for this place, this one was a bit tricky for me, but I already figured it out, right? So I mean, my pipe goes like this. This is at 45 degrees, right? Like I say, it's shorter distances usually better. Press space bar to repeat that command, and then this flows out through here. So this goes here, and then okay, joins here, at 45. Okay, this is 45. So I'm just going to extend it. So this is trim. Right, press shift and then do this. It does the reverse, the opposite, which is extend, right? So now this is a very simple system. There's no other fixture anywhere, right? So now I could have sent this out through here, but I just choose to do it this. Okay, let's extend this. Okay, let's extend it in another way. So I will lengthen it reach here. Okay. So now this is a case where they're going to share one vent, right? Okay. So now this is now we are done with this. What's the next step? Okay. Now um this building from what the information I got from the client is not has its own, or the client is ready to get his own septic tank. So this is not routed to the municipal sewer, even though I'm still going to use like the same sizing systems to do that. So now what is next? According to our checklist, next is to assign DFUs. Right, let's go to that project. DFUs. Okay. So to do that, we go to the page that we have our DFUs on. So this big project is in California. So that's why I use this particular California table. Right, and if you notice, it's not very different from the other one. So lavatory, we have just one lavatory, we have one WC, and then we have two floor drains. Right, and we indicated DFU loads here, and then based on the quantity, you multiply it and get the total, give you the total DFU, which is 9, and then you also take note of your trap size. This is important in cases where you need to size the grease interceptor. But even that aside, you just need to state this too, right? So, and it's also stated in those tables. So let's go back to our model. So what's our next step? Our next step is lay out our piping, which you've already done, and indicate the slope. So let's check what the slope for this project is going to look like. Let's go to that chapter. Okay, this is where we are. So I mean 9, our total DFU is 9. So I mean this works. This works. I like to avoid this unless I have to use it. This works. So 9 will be somewhere here. Right. So it means a 2 inch pipe is okay. Right. Let's go back to our project. A 2 inch pipe. So it means, and that 2 inch is going to be the largest pipe available in that system. So this is going to be 2 inches. All of this is going to be 2 inches. Now this one that is serving only this place can be smaller, maybe 1 inch. Let's see, or it can still be 2 inch to be on the safe side, because there might be cases where you need to like add a system to this. Now this should also have a floor drain too. Have a floor drain. Let's see, somewhere here. If you notice, even close to this one, you can put a floor drain here and make it to like pass through this guy, so it still serves out as one too, right? So a floor drain. Now floor drain is unlikely. I mean, it's not very um um it's not set in stone, it's not very compulsory, but just to make your system standard, you can add a floor drain here so it flows out through here. I didn't want to give it its own pipe because that is like, I'm trying to do like economic use of materials, right? And it's close by, right? And also I didn't also mind using this, although standard always it should be a 90 degrees or 45 degrees somewhere here, right? 45 degrees helps to give a better design or a standard design, right? So now we trim this too. Oh shit, I made a mistake. Okay, let me extend this first because it does not reach. Okay, now you trim it, it stops at that boundary. So now this one needs to be trimmed. Okay, see, it's not reaching. Okay, okay, and trim this also, right? But I can decide to take this out if I want to, right? It's just example purposes too. Okay, so moving on, what are we supposed to do next? It's going to be a simple project. So design venting. Now okay, layout piping, size sanitary pipes. You size the pipes. Okay, let's indicate the sizes on the that that project, right? Okay, so our main pipe is 2 inches, and then just to avoid assumptions. Oh, what am I doing? 2 inches. To avoid assumption, come and place it. Oh, that's a mistake. Okay, copy. Just add it here. Okay. Now I'm just going to maintain 2 inches across everywhere, right? Because if you notice this, you notice the, see here, not here. What am I looking for? If you notice here, you have a minimum of 1/4. So I mean, to be honest, if I just use your normal 2 inch pipe. In fact, you even need to increase it to 3 inches because of this guy. So you see, so that place now, because, and usually once you have a minimum of a large um or any particular size, your main pipe needs to be that size or greater, because it can't flow from a larger to a smaller pipe. So because of this, now there'll be a 3 inch. So I'm just going to set all of them as 3 inches. So I mean, the only case I would have used 2 inches would have been if we didn't have any lavatory. But for specifically for lavatory and because of solid waste, we usually need to increase it to 3 inches total, like everywhere. So this one can stay at 2, right? And then these two can copy it, right, to here. Okay. So moving on, what else? We've sized our pipe. Next, we design venting. So let's vent our system. Okay. It's going to be simple venting. So now I talked about how this is going to be a a a shared vent. There's a name I called it. It's not a shared vent. There's a name I called it. Yeah, a common vent. Right, that's going to be a common vent, and it's also going to have a vent stack. We'll talk about that shortly, right? So yeah, it's going to be a common vent. Now I've added these keynotes. You see what it means later. So this too is also a keynote, and if you notice, I've also indicated this, which indicates like where the pipe gets touched, where it meets the fixture. So this is like a kind of accessory, or plumbing accessory, basically these two, right, which is a minimum of 3 inches in diameter, right? And what again, now I've also added our floor drains, right? So this is our floor drain, and then is it these two? We'll see what this two means shortly. Then this one too. So now this is just the venting line. This is going to be a circuit vent, because the vent, and I remember saying that we must always vent floor drains, right? Even though they don't have heavy flows, because one day they might have. You never know. It's usually good to design for the worst day possible. So this line indicates the vent line. This is vertically up into the wall. Within this is a wall, right? And then within that wall, it meets up here and then it goes up. Let me show you what now number one means. So those different keynotes I've added, right? Let me show what it means. Now, these are the different keynotes. So one means 3-inch vent to the roof, which is here, like in this case now. So this is a wet vent, and then the air goes up into the roof, right? And then what again? Terminated with a weather cap, right? Because if there's no weather cap, it's going to be open, and then anything can fall in from up there. So there has to be a weather cap, and that is also shown somewhere on our plumbing detail. Where is it? Weather cap. It's not here. Usually, okay. Is it this? Okay. This is what it looks like. This is what the weather cap looks like. Right. You see, this is the vent stack, so it covers it, but it doesn't like cover it airtight. It covers so that the air can come out or the gas can come out from under. It's basically to just prevent it from falling in. Right. So let's look again at, okay. Now 2 stands for my own keynote, right? You could have more based on what you have, but this is just a coincidence. 2. So 2 stands for the size of that sanitary line. I've noticed for anything lavatory or sink, it's usually 2. That's what this 2 stands for. And also it's also the same for um floor drainage, because I mean you see that it matches with our sizes here. So 2. So I mean that's why you have minimum of 2-inch pipe, right? And then 3 too. for sanitary line. Most times for WC is usually 3, right? The size of the pipe is usually 3. Now the venting, if you also notice, this one is usually for venting. So these two um, vent pipes that are traveling vertically in the wall, they now meet at this point and then they go up into the roof, right, at this place. And at this, so there are going to be two um, exits or two vent stacks going up into the roof and being terminated here and here, right? So now the thing is that why I had to make this a circuit vent or a shared vent is because we wouldn't want to be puncturing the roof too many times. If you had many fixtures, imagine puncturing the roof for all the fixtures. So anywhere you can, you try, and that's where circuit vent really shines, because you might need to like use, but as far as you're able to like maintain that they're all like leaking out or they're going like falling out through that pipe, that works, right? Just ensure that you create that circuit so that at every point in time they have like where to escape through, right? And then if also that slope you spoke about, if you notice it, you can notice it here. And there's a slope here, there's a slope here, and then this one that's carrying a large amount of all of them. You see the slope here is a bit steeper, right? Okay. So what else in our list of um okay. So next, check code limits on trap arms, right? This you don't always have to check it. You just need to have like the standards, right? This shouldn't even be here. Then select equipment. In this case now we didn't need interceptors or pumps because there's no need for it. Now I'm going to send my file to my architects and structural engineers, right? So I think you are good. So by next class, we're going to look at another project and see how we can. I mean, if we had a case, I think we can even do that today. If we had a case where we had maybe a kitchen, a full kitchen, and then we had like um a what do you call it, a sink or other types of fixtures in that space, right? You can just easily connect them and then indicate the location of our um Breeze Interceptor. Let me see if I can find a project like that. So this is a project where it is a commercial kitchen, right? Now this stands for floor sink, right? And this is the kitchen section. So you just see all these pipes coming in and then it enters into the Breeze Interceptor. Now, based on the total GPM of all of them, it will give you an idea, multiply by your 30 minutes or 1 hour, give you an idea of the size of Breeze Interceptor you select, right? So this is just an example. So I mean, we'll look at it more in detail. You know how you just list out the way we size our water heater, where you just list out your existing, where's that water heater? Okay, something like this. Just list out the existing equipment that are flowing into that place and then to get your total GPM or GPH, and then you size accordingly. So that's just basically the difference, and then you select your equipment if you have to, right? So thank you for turning up or showing up, and I hope this class was easy to understand for you.